Hello, you students of calculus. Today, we're going to work on basically just kind of reviewing some integration rules and maybe addressing a couple new techniques to integrate. So our objective is going to be just to do that, to review procedures for fitting an integrand to one of the basic integration rules. And then at the very end, I'm not going to write them, but there are rules in your book. And then I guess if you don't have your book, I can write them up for you, so just send me an email if that's what you want. But at the end, we're going to kind of have a list that covers all these basic techniques. So we'll start with these three similar integrals, and we'll kind of address how each of them has a distinct problem. And I don't want to write in this. Let's do blue. All right. So in the first one, we have the integral of 4 over x squared plus 9 dx. Okay. Now in this one, you know that 4 is a constant. You can factor that out and just rewrite that as a constant. Multiple 4 times the integral, and we're going to be left with 1 over x squared plus 9 dx. Now this one might seem a little tricky at first. Okay, you might be thinking, well, this isn't definitely not going to be a... You probably think that this might be a natural log rule, but that's not going to be the case. You can rewrite this, however, as 4 times the integral of 1 over... And you're going to kind of want to take a look at those trig ones again. Those ones I'm assuming you guys might not have memorized super well, but I would encourage you to do so. We can rewrite this as, well, the quantity x squared plus the quantity 3 squared, where this x would be our u and this 3 would be our a value. And you should recognize that this is, well, this becomes an arctangent problem. So then this just becomes 4 times... Well, once I recognize that, it's going to be 1 over u, or excuse me, 1 over a, 4 times 1 over 3 times arctangent of u over a, x over 3, plus c. And we'll just multiply these two constants up front. 4 times 1/3 is 4/3 arc. Wow. This should be arctangent above there. Arctangent of x over 3 plus c. So that one just comes down to recognizing what type of problem it is. Make sure you know that those trig integrals. All right, now in this next one, well, the first one you might have thought this is kind of like a natural log rule, but why isn't it? And if you look at the denominator, the natural log reversing that rule, it's like u prime over u, right? Or du over u. Well, if u is x squared plus 9, then du has to be 2x. Basically, we need a linear term in the numerator. And in example B, we have just that. We have the integral of 4x over x squared plus 9 dx. I'm going to do dx up here. Okay, but it's not quite exactly the derivative of our denominator. It's very close to being u prime over u. It is in that form. But we can rewrite this. Well, if it was u prime over u, this numerator should be 2x. It is 4x. So what we can do is just pull out that 2. This is the same as 2 times 2x over x squared plus 9 dx. Okay. And, well, that's going to be helpful because that equals, well, now we have u prime over u, which means this is 2 times the natural log of u, which is x squared plus 9 dx. So it should just be 2 ln of x squared plus 9 dx. And hold on, we're doing an indefinite integral. Also, I evaluated that. I don't know why I have that dx anymore. It should be plus c. Excuse me. Since it's an indefinite integral, we can have some constant here once we do the antiderivative. All right, now, one thing I want to address, why is there no absolute value sign here? We should have an absolute value sign here, shouldn't we? But if you remember, well, I guess a couple different things. Technically, 2 times a natural log is the same as that natural log if I were to move this up here and square that value, which would then effectively means it doesn't matter what I plug in here. Or you could also consider the fact that, well, what am I doing inside this absolute value? I'm taking some quantity and squaring it. So no matter what quantity I'm putting in, it could be a negative, I'm always going to get a positive anyway. So for either of those reasons, you can drop the parentheses. Now in example C, we have 4x squared over x squared plus 9 dx. You might be thinking, well, what the heck do I do here? Okay, now remember, when the degree of the numerator and the degree of the denominator is the same, you're going to have to do some long division. So we're going to actually perform, well, 4x squared divided by x squared plus 9. So do some long division. We have 4x squared. We're dividing that by x squared plus 9. Well, how many times does x squared go into 4x squared? And the answer is 4. Okay, take this whole thing times 4. We're going to subtract that. Well, 4 times x squared gives me 4x squared. That's exactly what we sought out to do in the first place. 4 times 9 gives me 36. Okay, so, well, 4x squared minus 4x squared, that's going to be 0. I'm going to be left with minus a positive 36, minus 36. So we have this remainder, and we're still dividing this remainder by x squared plus 9. So this becomes 4 minus 36 over x squared plus 9. And the reason we did that, you might be thinking, Mr. Wynant, this just looks like it's going to be more complicated. But the reason we do that is because now it's going to be easier, I need my integral there, to integrate this. This is the same as, well, once we perform this long division, we know 4x squared divided by x squared plus 9 is the same as 4 minus 36 over x squared plus 9. That entire quantity dx. And now we can kind of take it piece by piece. This is the same as the integral of 4 dx minus the integral of 36, but 36 is a constant. I can write that out front. Minus 36 times the integral of 1 over x squared plus 9 dx. And this integral should look familiar. 1 over, in parentheses, x squared plus 9 I can rewrite as 3 squared. You should recognize that's just, again, going to be an arctangent problem. Okay, well, the antiderivative of 4 is just 4x. That's pretty easy. Minus 36 times, once again, reverse this. This is going to be an arctangent type of thing, so it's going to be negative 36 times 1 over our a value. Our a value is 3 here. So 1 over 3 times arctangent of u over a. Our u is x. Our a is 3. And on all of this, we're adding some constant c. Simplify this down just a little bit. This is 4x. Minus 36 times 1/3 is the same as 36 over 3, which is 12. So minus 12 arctangent of x over 3 plus c. So just a crash course there a little bit, kind of went a little quick, of just a review of some techniques we've done so far. And this basically, this whole unit is going to be a review with a little bit of new material. And I'm going to continue to work relatively fast, so I encourage you to pause the video and try to work through these before I get to them, just so you aren't just kind of lax and watching me do something. Make sure you're engaged, you're actually trying and maybe even failing, which is good. You learn from kind of attempting and making mistakes. So make sure you're pausing the video, working through as I go through it as well. Okay, so in example 2 here, we have no longer are we working, I guess in this specific example, we have a definite integral, so we're going to have to actually evaluate this thing. Okay, but we're going to have to do something. We have x plus 3 over the square root of 4 minus x squared dx. And what we want to do here is we have this x, we have this plus 3. We can break this up into the sum of two separate fractions. This is the same as doing, well, x over 4 minus x, the square root of 4 minus x squared, plus its own quantity, 3 over the square root of 4 minus x squared. So let's do that. And then I'm just going to, we know we're going to integrate those two separate things eventually, so I'll just tackle that in the one step. So this is the same as x over the square root of 4 minus x squared dx plus, integral 0 to 1, 3 over the square root of 4 minus x squared dx. Okay, well, how the heck does that help us out? Okay, well, here's what you're going to want to do. In this right one, you might be able to recognize that one's not too bad. We can maybe make that into a trig type of thing. We'll get to that in a little bit. This first one might be a little trickier to see intuitively what's going on. But what you can do here, you can write this as the integral of 0 to 1. And then I have a square root in the denominator. Technically, 4 minus x squared, that quantity, is being raised to the 1/2 in the denominator. Bring that up to the numerator. You make its exponent negative. This is the same as x times 4 minus x squared to the negative 1/2 dx. Plus, then this is a constant 3. I can pull that out. 3, 0 to 1. I'm left with 1 over the square root of 4 minus x squared dx. This is going to be, and now what we just did here is, what the heck is going to go on in this first part here? This first part that I'm going to highlight here. What's going on there? And I don't like that, and immediately I'm going to erase that. All right, but what's going on in that first part? And after kind of looking at it for a while, you might be able to recognize this is kind of like we're reversing that chain rule, or maybe even just a power rule. If you look at this 4 minus x squared, if that is the quantity that is inside these parentheses, well, we know that we're going to have, for the derivative of the chain rule, we know it's like the derivative of the outside with respect to the inside times the derivative of the inside. Okay, well, what is the derivative of the inside? And the derivative of the inside is negative 2x, which would be nice if this value here was negative 2x, but it's not. So we're asking, well, it must have had some coefficient then. What times this, or I guess we're asking what times this, what times negative 2x, we want it to be negative 2. Well, what times negative 2 would give me, we had positive 1. And the answer is negative 1/2. If you take negative 1/2 times negative 2, you would get 1, which is where we started. And the reason we're making this negative 2x is because we want the derivative of the inside. Negative x squared, the derivative of that is negative 2x. So that kind of takes care of that. So we're just going to rewrite that. And then, well, I know that once I do that, if this is my quantity u, then we'll just kind of reverse the power rule. You add 1 to its exponent and divide by that quantity. So you add 1 to the exponent. Well, negative 1/2 plus 1 gives me, well, I'm going to have 4 minus x squared to the negative 1/2 plus 1 gives me to the positive 1/2. And then you divide by that quantity. Well, we're going to divide by 1/2. That's the same as multiplying by 2. And keep in mind, once we do that, this basically effectively gets rid of this negative 2x once we do the antiderivative as we're doing right here. So that's going to be gone. And we're left with this constant negative 1/2. So we have negative 1/2 times 2. Well, that's just going to become negative 1. So we have negative 1. We've done the antiderivative of this. Basically, we've just reversed the chain rule. So we're going to have negative 1 times 4 minus x squared to the 1/2 plus 3 times, now, this one right here, you have 1 over the square root of 4 minus x squared. I can rewrite this 4. Notice that the perfect square is 2 squared. I can rewrite x squared as x, that quantity, squared. And now you recognize I have 1 over the square root, or I guess you could recognize if u is x, then du is 1 dx, and you recognize you have du over the square root of a minus x squared. That's going to be an arc sine problem. So this becomes 3 times the antiderivative of that is going to be arc sine of u over a of x over 2. And keep in mind, this is a definite integral, so we are evaluating this whole thing from 0 to 1. Okay? Now you plug that in, you should get, for that first quantity, you should get negative 3 when we plug in 1, negative, whoops, not the square root of negative 3, that'd be imaginary. Negative root 3 plus pi over 2 minus, you plug in 0, you should get negative 2 plus 0. This is going to be about, really, this approximation is fine, 1.839. So this problem, kind of, remember, you got to break it up and then address these two things on their own. The one on the right essentially becomes a trig antiderivative. One on the left is just a power rule, kind of reversing that chain rule, if you will. All right, example 3. Now, we want to find the antiderivative of x squared over 16 minus x to the 6th. The square root of that, I should say. Square root of 16 minus x to the 6th dx. Right away, this might not look intuitive in what you have to do, but you might kind of recognize, I sort of have, in this denominator, I sort of have a trig rule going on. So we can rewrite this as the the integral of x squared over the square root of, well, I can rewrite 16 as 4 squared minus x to the 6th. How can I rewrite that so it's a quantity squared? Well, that's the same as x to the 3rd squared. And how the heck is that helpful? I still have dx here. Well, if this is going to be a trig antiderivative, or a trig integral, if you want to call it that, we have to have du over, some quantity usually involving an a and a u where we're squaring those quantities. Okay, but what would du be? Well, if we choose u equals, in this case it would be x to the third, that would imply that du equals 3x squared dx. Now what's the problem here? Right now it's just x squared. We want it to be 3x squared, which means we can rewrite this as, this is the same as if we want it to be 3x squared times dx over the square root of 4 squared minus x to the third squared. And, well, we have to keep this the same as the original inequality, or excuse me, integral. That's the I word I'm looking for, which means we need 1/3 out front. Now we have an equivalent statement, and we have something that's going to give us, well, something in the form of this trig integral. And now we can recognize, well, this is going to be 1/3 over u is x to the third, du is going to be 3x squared, so this is 1/3 integral of, well, du over the square root of 4 squared. You could write a if you want a to be 4, but we're just going to leave it as 4 squared minus u squared. And you can recognize that that is going to be an arc sine problem. So this is just going to be, we still have this 1/3 out front, 1/3 times, well, arc sine states that it's just arc sine, and then u over a. Our u value is x cubed, so x cubed over our a value of 4 plus c. And that's all that one takes. Okay, so some of these problems are easier to recognize. Some of them you have to do a little bit of work to get it in the form where you can recognize what you can do the antiderivative of. All right, an example 4 here. This one is kind of tricky. If you look at this one for a while, you might struggle to find what you have to do. It doesn't seem to fit the rules. However, it kind of fits the log rule if you do something a little tricky. If it's the log rule, it should be u prime over u, right? Well, what is the derivative of the denominator? 1 plus e to the x. Well, remember that the derivative of e to the x is just e to the x. So if u equals 1 plus e to the x, then we know du is going to equal e to the x dx. Well, what the heck? That doesn't even look like anything we need, Mr. Wynant, and you're exactly right. Now, here's something we're going to do, and it's a little bit tricky. We are going to change the way this looks without changing the actual value of this statement. We can rewrite this quantity as 1 over 1 plus e to the x, but we can both add and subtract this e to the x in the numerator. And you might be thinking, why the heck would we do that? And here's why you can do that. We didn't change the value. Technically, e to the x minus e to the x gives us 0. This is the same exact statement we had at the beginning, except I need my dx here. Okay, but now what we can do is we can split this up. This is the same as the integral of 1 plus e to the x over 1 plus e to the x, and I still need my dx, minus, and then I have this quantity here, minus e to the x, the integral of e to the x over 1 plus e to the x dx. And the reason we do that is because, well, now this becomes pretty easy to do the antiderivative of. This quantity is just going to be 1. This is the integral of 1 dx minus, well, you can recognize this as going to be a u prime over u. So, well, now we integrate. The antiderivative of 1 dx is just x. That one's pretty easy to do. Now, this is going to become a log problem. Okay, so we have negative e to the x over 1 plus e to the x. Well, this is a u prime over u, or a du over u. This is going to be minus the natural log of, in absolute value signs, 1 plus e to the x plus c. But I want to talk about something here. What's in this absolute value sign? 1 plus e to the x. No matter what value I plug in there, well, what is e? E is just some constant, right? Well, if I raise some constant to anything, I'm still, and I guess more specifically, it's a positive number. And if I raise a positive number to anything, even if I raise it to a negative exponent, that's still going to be a positive number. It could be a really small positive number, but no matter what, it's going to be a positive number plus 1, which means no matter what, inside these absolute value signs, I'm going to have some positive number. I don't know why I wrote that arrow. I was going to write stuff, but I basically just said everything. So since no matter what, whatever I plug in for x in here, it's going to be positive, I don't need that absolute value sign. This is just the natural log of, in parentheses, 1 plus e to the x. And then this is an indefinite integral, so plus c. So the reason we're going through these and talking about that absolute value sign, if you ever see something where the absolute value sign is parentheses, and you have absolute value sign, you know, well, why didn't I address that problem? Think about what's going on in there. Sometimes you can drop the absolute value sign. All right, example 5 here is somewhat tricky. It is somewhat tricky. So we have cotangent of x times the natural log of sine of x dx. If you look at your trig, or if you look at your integral thing, you might be thinking, well, this kind of looks like a cotangent of u problem, but that's not going to be the case. We have a whole entire thing of ln of sine of x going on. That's not going to work. Okay, now, you might be trying to do some u substitution. You probably would think, well, it doesn't seem to fit a whole lot, but what if we consider a couple things? Well, what if u equals cotangent x? That might be one option. Or u could be the natural log of sine of x. Okay. Well, consider both cases. If u is cotangent of x, you have to think about what your du would be. Okay, well, if you use u and you say, well, u equals cotangent of x, du, that's not going to work. That's not going to give us the natural log of sine of x. We don't want that. But what if I choose u to be ln of sine of x? And if you choose this one, well, if u equals natural log of sine of x, what does that mean du equals? Well, we know that the derivative of the natural log of something is u prime over u. Well, u prime over u, well, what's the derivative if this is u, I guess? We're using u within u. The natural log, it's the derivative of that thing divided by that thing. Well, this is going to be, well, what's the derivative of sine? That's going to be cosine of x over that thing, which is just sine of x. And what the heck does that look like? Well, cosine of x over sine of x is cotangent of x dx, which is exactly what we have here. So this just becomes a power problem, essentially. We can do some u substitution, and we can write this as the integral of, and then I'm going to rewrite the entire quantity, ln of sine of x times cotangent of x dx. But if we used u substitution, we can recognize this is going to be du, this is going to be u, so we have the antiderivative of u du, which is just going to be, basically you treat u and just do reverse the power rule. So this is going to become u to the, well, it's an original exponent of 1. I add 1 to that, so 1 plus 1 is 2. U to the second, and then you divide by that quantity, divided by 2. And this is going to equal, and then dividing by 2 is the same as multiplying by 1/2 times u squared. And then you just plug in what u is. This is 1/2 times u, and I guess I should have a plus c here once I drop that integral, plus c. I need another plus c here. It's an indefinite integral. 1/2, and then what's our u value? Well, u is this quantity, the natural log of sine of x. We're squaring that, plus c. That's our final answer. Okay. So on that one, you kind of just, you have to identify what your u is, what your du is, and work from there. All right. Now, this last one, you're going to have to know some trig identities. We want to find the integral of tangent squared of 2x dx. So, well, this again, might seem like it doesn't fit anything. If you look at your integral sheet, there's nothing for the tangent squared of u. But there is something. There is something for secant squared of u. Well, okay, cool. How the heck does that help us here? And this is where you need to recognize some trig identities. There's a Pythagorean identity. There's a Pythagorean identity. Yeah, I don't like rainbow. There's a Pythagorean identity that relates the quantities tangent squared of some value and secant squared of some value. That states, well, tangent squared of whatever that value is, let's say theta, equals, and I guess you might see plus 1 equals secant squared of theta. Well, what you can do here is we want to get this to look like secant squared of something because we know what the derivative of secant, or the antiderivative of secant squared of something is. So what we can do here is just rewrite this and substitute our value. This is the same as tangent squared theta. And if we subtract that one, this is the same as secant squared of theta minus 1. Now, this is just the Pythagorean identity theta. We're actually using 2x. That's going to be our kind of like our theta or our u. So, the reason we're doing this is because we know that the antiderivative of secant squared is tangent. We can evaluate that. So, we're going to go back up here. And using this Pythagorean identity, we're going to rewrite this integral. This integral is the same thing as the integral of, well, tangent squared of 2x, tangent squared of something is the same as secant squared of that something minus 1. So this is the same as secant squared of 2x minus 1 dx. Okay, now, we're going to use some u substitution just to clean things up. We're going to let u equal 2x, which implies that du equals 2 dx. Okay, because, well, the antiderivative of secant squared of u is tangent of u, or I guess secant squared of du is tangent of u. Okay, so we can rewrite this. This is going to be the same thing as secant squared of 2x dx. Look at that on its own. Minus 1, the integral of 1 dx. Okay, and then you can recognize, you can do u substitution or you can just recognize what it is. You don't have to. I'm going to plug it in just so we can see. This is the same as secant squared of, well, if u is 2x, then du is 2 dx. So this is u times, we don't have that dx, which means, well, this would be the same as, and I guess, you know what? I don't really want to do u substitution. Let's just do, this is the same as secant squared 2x. Now we want it to be times 2 dx. So let's just write that, times 2 dx. But I don't want to change the value of this statement. So what do I have to do to not change the value of the statement if I'm going to write this 2 here? I have to multiply out front by 1/2. Okay, so we're just going to rewrite the way it looks without changing its value. Minus, well, this 1 dx, we can take care of that in the end. We already know what that's going to be. Okay, so what I've just done is this quantity, whoa, this quantity here is our u, this quantity here, this quantity here is our du. And what is the antiderivative of secant squared u du? And the answer is tangent u. But we still have this 1/2 out front. So this becomes 1/2 times the tangent of u. Guess we can write that. But we know that u is 2x, so we'll just plug that in. Tangent of 2x minus the antiderivative of 1 dx is just, the antiderivative of 1 is just x. And then this is a definite integral, so plus c in the end there. So our final solution is 1/2 tangent of 2x minus x plus c. Are there any like terms we can combine? No, that's as far as we can go on that one. All right, now, on the page on the bottom of page 521, there is a list of the basic rules of integration. I would encourage you to check that out, maybe write them down, commit that to memory. On the page 520, there's also a list of basic integration, I guess a list of basic integrals, or I guess more complex integrals. There's kind of like a cheat sheet there. So I'd encourage you to check those out. Make sure you are familiar and comfortable with these types of things. The more you memorize, the less time you have to worry about figuring things out. So that is all we are going to do for these notes. Have a good day, everybody, and as always, stay safe out there.